Everybody, whoa, and the microphone is hot again. I'm going to turn the mic down a little bit so we don't blow out the speakers. All right, so thank you very much for coming. Hey, I really appreciate everybody showing up for the guest lecture. So here's what I want to give you right off the bat. Number one, this is one of a long series of guest lectures that have been in COGS 108 over the years. If you go to this YouTube channel, you will see a bunch of past lectures that you might be interested in. I don't know, maybe you like Roblox and you'd like to see the Roblox team talk about that. Or maybe you'd like to get some career advice from working data scientists and you want to go see the Build Your Career in Data Science authors talking about how to build your career in data science. Okay? So there's a variety of really cool appearances that have happened over the years. Take advantage of this resource. Okay, next up, we're going to have Kyle Shannon talk to you about a data science project he's working on. Now, Kyle is amazing. Not only is he an instructor in cognitive science and the Data Science Institute here, he is a working data scientist. He does this stuff for reals, unlike me. So he knows what's up. And he's going to talk you through a project that he's working on and have you provide your input on this project. I think we're probably going to have some time for Q&A at some point. Yeah, like 5 or 10 minutes. 5 or 10 minutes at the end. All right, so I'm going to give the mic to Kyle in 1 second, but before I do, now that you've all had a chance to note the past things, I'm going to give you your one you really here for. This is how you check in and get your extra credit, okay? So, without further ado, here is Kyle. Thank you, sir.
No problem. Thank you so much, Jason. All right, can everybody hear me? Mic's all good? In the back, all good? All right. Okay, so as Jason probably over eloquently pointed out, I do teach here. I really like working with students, which is a big reason why I was very excited to come out here and talk to all of you. But I also do work in data science all day long. That's my main job. And so what I wanted to talk to all of you about is what a real data scientist kind of does on the job when building data products. And so my promise to all of you at the end of this talk is that you should know a little bit more about what a data product is, how a data scientist works on a data product, and how they find value for customers or end users or whoever's going to use your data product. It's a really important thing. And if you don't know what a data product is, think about like Google Maps. It's a product like that, or you can think of like a healthcare dashboard that a doctor might use when trying to help work with a patient. It's something where it's a technological piece of software, typically, and the main point of it is to help you with decision-making processes. So with Google Maps, you want to kind of find the fastest way to get from A to B. It's really data and machine learning and algorithms at the heart of that product that's helping you to achieve some sort of goal. And that's a completely, profoundly different paradigm from building software that allows you to do things like CRUD operations, create, update, delete, like working with bank. If you log on and check like, oh my gosh, how am I going to pay my bills today? The cost of living in San Diego is just so high. Like you're not going there and trying to use some sort of like financial data to make a decision on whether you can afford a rent. You're just trying to use the banking system to move money around and like pay a bill. That's a completely different way of using software. It's the way that you're all typical. It's the type of software you're all typically used to using. But a data product is much different. It's not only much different from your point of view, but it's inherently, fundamentally much different from the practitioner, the technologist, the software engineer, the back-end side of things. So what I want to explain to all of you today is how we kind of build data products. I know 50 minutes or 40 minutes if you have Q&A is not a ton of time, so we're going to kind of go from a very high level, and we'll pick a few places to kind of go in depth. And I think the best way to do this is on the Blackboard, because this is not a project that I have finished yet. And I kind of want to make it more interactive and something that's kind of fun, and to show you how I think through things and think through resolving problems. And all of that's much easier to do if we're working on the Blackboard kind of live, rather than just showing you pre-canned slides of things that I've done. So today, I'm going to introduce you a little bit to the background of the project. I'm going to talk you through some of the domain expertise and some of the requirements of the project, some of the data gathering challenges and how we go about doing that, some of the feasibility studies and some of the data science studies that we had to do to work on this project. I really want to spend a lot of time on the architecture of the project, because that's something that you don't get a lot of exposure to in classes at UCSD. And then I want to talk to you about the value proposition of such a product, which is like really where the whole show is. Like, if you don't have a value proposition for your product, then you don't really have a product, because nobody's going to use it because there's no value. So value begets product, which begets data scientists being paid lots of money, which is why we're all here, right? It's to get jobs to make lots of money, maybe. But there's no doubt that data scientists do make a lot of money, and the reason why is because this shit is very hard to do in the real world, and it's not one size fits all. So it's a culmination of years of experience and years of paying attention in class to instructors like Jason, who know a lot about what they're talking about, because they have, in turn, years of experience. OK, so without further ado, let's talk about background. Who here knows how bus stops get created, like the decision to put a bus stop right here? Does anybody know how that decision gets made? Anybody? But we all know what a bus stop is, right? We all use bus stops. We've all seen it. We all take it for granted, but we don't know how they actually are constructed. Now, you could probably imagine how a bus stop might get, like a bus route might get decided in an urban area, because it makes a lot of sense. You have a lot of people gathered into a small, dense area, and you've got to get them from point A to point B. This includes places of living, places where they work, places like the stadium or the hospital. That makes a lot of sense intuitively. But what about buses in a rural area where you have a dispersion of hundreds of square miles, and you've got to service people along a great wide area? How do you even think about how to create a bus system that goes into small towns, goes to community centers? How do you know that you've made a good bus route? How do you figure this stuff out? And this is a challenge that is kind of plaguing all of rural America right now. It's a really huge issue, because there's only a limited amount of resources, only a limited amount of buses, and there's many, many people. About 32% of Americans still live in rural areas across the United States. So how do we help these 32% of Americans get where they need to go when transportation accessibility is a huge problem? This is the challenge that me and my data science team is currently working on in northern New York with 3 counties. And when we talk about like northern New York, like everybody thinks New York City, but real northern New York is like 6-hour drive north of New York City, right near the Canadian border. So this is about probably like 1.5 million people. And these people usually take about, I think of the bus system there is about 200,000 unique people taking bus transit services through all the different small places and towns in northern New York in these rural areas. So this is a problem and a project that has the ability to impact many people, and we can do a lot of good. So that's the background of this project, is we're going to try and help these counties. Particularly, there's this job called a mobility manager. And the mobility manager, it's their job to try and determine if the bus routes are good and how they should change, which is an immensely difficult job. So we're going to help them, because they're the domain experts. And because I, like you, don't know how the hell a bus route is created and where a route should go, I'm not a domain expert. I've got to consult and work with these domain experts and do my own research to figure out how to solve this problem, or at least how to help enable them solve their own problem. So this is the background. This is the story, and this is why this is an important project to work on. And it's one that's sufficiently complex that involves a lot of data. OK. Any questions so far in the background or what it is that we're trying to do? Very, very high level? Everybody's with me on the same page? OK. So I started talking a little bit about domain experts and requirements and why they're so important. Domain experts are the really, like their importance to a data science project can't be understated because there's so much inherent value in what somebody who has knowledge of a domain can bring to you and the data that you're looking at. It can't go without saying how important they are. If I want to try and understand how a bus system and a bus route is currently built or configured, or understand the data they're currently collecting, I have to rely on people like that. I have to interface with people like that to learn these things. I'm not going to go to St. Lawrence County in upstate New York and like push in the door and be like, hey, where's the data, everybody? You know, give me all this crap. They're like, who the hell are you? You got to go through the domain expert to get access to all this stuff, which means you got to become really good friends with that person, and they have to believe that you're trying to be a champion for their cause. If not, you're kind of just a roadblock. And that's even considering the fact that they want to do a good job and make change. Sometimes you get these like bulwark people who just don't want to do things, or maybe they just feel ineffectual, or they don't have the ability to do these things. So you really have to be good at working with a whole broad range of people and having empathy for these domain experts and understanding what value they can bring to the table and helping them realize that. So you work with these domain experts and you start to really quickly figure out what are the requirements of the project. What kind of data are they collecting? What kind of funding do they have? How do they want to use this product, right? Like, I'm building a data product. I'm sure as hell not going to be creating bus routes. That's not my job. That's their job. So I'm building a product for them. And the product I built for them might be completely different than the product I built for myself, because I'm much more savvy technological-wise. I live and breathe in this stuff all day long. This person, not very savvy. I had one domain expert once, a CPA who's working for an organization. Right? They have links to websites. And do they use bookmarks for the links? No. No. They literally take their links and they copy-paste them plain text into a Word document and save it to their desktop. Right? And this is a college-educated person who is in charge of, you know, a lot of financing for a company as a CPA, and this is, you know, what they do. So there's all sorts of people that you're going to meet out there, and you have to be prepared to work with all these people and their different capacities and capabilities. It's really important. Data science in the classroom is really configured towards helping you understand process and how you solve problems, but it's impossible to prepare you for things like the real world, where you have internships and stuff. But you have to be ready to be able to work with people like that, and to work with people who, their complete idea of what technology is and how to do things are 100% different from what yours might be. These are really important things to remember and understand. But when we're going to start, circle it back to this data product that we're building, in order to kind of understand what product we're building, I need to understand what the requirements are. I need to understand how much money do we have, how much funding is there, how much long-term funding is there, right? Like, it's not worth building something if, like, 2 years down the road, which funding dries out for this project, there's not going to be any additional funding. Like, who's going to take care of this product? Who's going to babysit it, update it, maintain it? These are all things you have to kind of think about. And they're really important, because if there's not going to be any maintenance for this project, then why should I spend my time doing it? If I don't see a future for this, there are many other problems out there to solve and work on. So you have to always consider these requirements. And requirement gathering is a really long and lengthy process and involves a lot of people who know nothing about data science, and the entire time you have to be trying to talk to them about what value you're bringing to the table and what value this project is going to bring. It's really important. So gathering requirements, really, really important. And right now, I don't even mean technical requirements. These technical requirements will come when we talk more about like architecture and that kind of stuff. I'm talking about just business requirements. How many people are going to be using this product, maybe? Who's going to be using it? These kind of questions. Is there sufficient even data to do this product? So this is where we get now from this idea of the importance of domain experts, and we start to talk a little bit about the importance of data gathering. Okay, so let's say that we've kind of gotten these list of requirements, and we'll talk more about these requirements when we get into the architecture phase. Both the technological requirements and the requirements in the project from a money point of view. Because the money and the funding does really drive the architecture, it's a case a lot of times of the tail wagging the dog when it comes to funding and architecture, especially when you're working in the cloud. But once I know that what are the loose requirements for building a product, and I kind of know what the domain experts are, and I have people on board, the next thing is to try to understand, like, what data do I have? What data do I need? And then this is where feasibility studies, data science studies kind of come into play. You start gathering data and you start looking at what you're doing and if it's feasible to do such a thing. So this would be a good time to start drawing some stuff. OK, so there's a lot of different data that comes through. One really important piece of data is called GTFS. And is this big enough for everybody in the back to read? Is this all good? Right? OK, cool. So GTFS is it's becoming now an international standard called General Transportation Feed Specification. I'm really bad at memorizing acronyms, but it was created by Google, and it is a JSON kind of document-y type thing, which lays out how transportation systems should be organized, how the data for them should be displayed and organized. Whenever you go to Google Maps and you look at the data for how long it takes you to go from A to B, what subway you might want to take when you're in New York City, or what buses you're going to take when you're in San Diego, all the data comes from a GTFS data standard. So I know that the routes for the current system of transportation in these rural areas is held in GTFS, right? That makes perfect sense. It's wrong, because using GTFS requires somebody who knows how to take data and put it into GTFS and send that to the stewards of the GTFS system. So, OK, do we even have GTFS data? Now, luckily, there was a company that was hired 5 years ago that came into the North Country. When I say North Country, I mean northern New York and the surrounding areas. And they got paid a great deal of money to take a bunch of PDFs, which were the bus schedules for these counties, and put them into a GTFS standard. And don't you know, a year after this was done, nobody friggin' maintained it. So you have all these old GTFS data now that's not being maintained. It's out of sync. People have gone back to doing things the old way, just creating PDFs online and pushing them out there for the bus routes. So, OK, we got to find funding first to hire some college student from Clarkson University who can go ahead and learn how to do GTFS. It's not hard to do. You just have to do it. So that's one thing that we had to do, for which we have a Clarkson University undergraduate who has done this for these counties, and they did a very good job. So now I have actual GTFS data. What other data might I think is important to have? Let's see. We're going to have, this is an interesting one, bus data. So this is like a bus. So you have bus data. What does bus data mean? On buses, there is a technology called bus transit system service feed or something. It's from, a lot of companies do that. There was a company called Paseo that these counties hired to create this data, and basically it does automatic ticketing systems, so when people go on, they can pay using their phone or their card a lot easier, and it manages counting how many people actually get on the bus, because before that it was the bus drivers who had a counter and would click on it, and sometimes they sneezed and would click twice. So we didn't have really great data, but now we're starting to have better data. These are coming online in the next month, so in about 4 months from now, we'll have better quality data for who uses the bus. And also, interestingly enough, it's got video feeds on there, so you can tell who's getting off and on the bus. Now, whether that's scary or not, who knows? Might be. But one thing that's very interesting about that is that buses in a rural area are not like buses in California or San Diego, right? If you're on the bus coming to UCSD and you see your stop coming up, and not stop, but you see like your classroom coming up, and you're like, hey, bus driver, can you just pull over real quick and let me off? Bus drivers will tell you to pound sand. But in a rural area, especially from the Amish community, you can tell the bus driver, hey, can you take a right and go down 1 mile and then drop me off? And they're like, yeah, sure, don't worry about it. Throwing the timetable completely off the rails. But this is a rural area. It's different than an area that we're living in right now. It works completely differently. So we have to understand from the domain experts that why we always see these anomalies of buses that are completely off schedule. It's because they're dealing with the Amish community. So, that information with the video analysis and with looking at Paseo's transit or ticketing system, we can get a better accurate count of what's happening with users who are riding the bus. So that's an invaluable piece of data that we're using or will be using. Another really important piece of data is going to be geographic data. So we can just put these as like, different databases and different CSVs, right? Anybody doesn't know, this is the international sign for a database of some sort. It's like a platter. So in this data product, I want to help people determine transit accessibility and if the route is good. To me, that doesn't just say ridership. I want to know about things like topography, right? I want to know, like, if you've got to walk up like 400 feet of incline to get to a bus stop, it is far less accessible to people living in that area than it is to somebody who has to walk down 100 feet in elevation to get to that bus stop. So topographic data is really important, as well as census data. I want to know who lives in these areas. I want to know what their socioeconomic makeup is. I want to know, is there an area where it's possible for them to drive a car or to carpool to an area like a transit stop, which has a lot of buses that come through it. So these are all data that comes from the US Bureau of Statistics and census.gov. I want to know about roads and all these different kind of geographic data. And this all comes from the US government, which keeps track of all this data. And it's all freely available. So now we have quite a bit of data growing that we're going to have to work with here. And I don't know if there's any other data I want to talk about. Yep. I guess there's also financial data and other stuff. But primarily, these are like the data sources that we might use for this kind of project. And you'll notice very quickly that there's a problem, right? So what's the problem with all these kind of data formats? Anybody? Yeah.
It's hard to combine different data from different sources.
Exactly. Great answer. Like, how the hell do you start to combine all these into a product? You've got bus video, proprietary data, you've got databases, you've got Excel spreadsheets and CSVs, you've got JSON data. They're also talking about data that falls into different temporal time units. They also have data talking about different distributions of land, like the census data comes in FIPS codes, it comes in zip codes, it comes in census tract codes. So this data is distributed in all different ways. So one thing we have to do is try and find a way to kind of bring all this together and be able to analyze it on the same scale. Luckily for us, everybody here knows what Uber is, right? Yeah? Okay, at least I have somebody who's interactive. Okay, so Uber wrote a library called H3, and this library, it's not complicated, but I could give like several lectures in and of itself how this thing works, but it wraps the entire world in hexes. So you have like something like this, and they, well, I mean, I'm bad at drawing hexes, but they wrap the whole world in hexes like this. This is a bad one, and then of course there's like a midpoint to the hex, but you can encircle the entire world in these hexes, and these hexes there's hooks in that library to go from lat long to hex. If a latitude and longitudinal point falls within a hex, and then it's got different ranges of hexes. So I think it goes all the way from encircling the world in a polyhedron, which would be like 15 or so of these hexes, but you have to. There's a way of doing that, but it goes all the way down to 1 meter width of a hex, where that'd be billions of hexes. And the library is very fast and allows you to translate between the different layers of hexes. So we know if we wanted to analyze a bunch of data on a standard scale, we've got to pick some sort of like stitching data set to go across a geographic area. So there's only 3 things that tessellate. There's triangles, there's squares, and there's hexes. Triangles are no good because the midpoint from one triangle to another triangle is not the same for all triangles, but it changes. Same thing for squares too. Like if I have a square and I have a square here, the midpoint between this, right? This is like x1 is not the same as its diagonals, right? So that would be x2. But yeah, these are not the same distance. But with a hex, they are. The midpoint from any hex to any of its surrounding neighbors is the same, despite my crappy drawing. So that's really a nice feature too. And I like the fact I said where it scales nicely. So the reason why this library was ultimately really great to use, though, is because I found from the domain experts and from doing research that a person is not willing to go and use a bus if they have to walk further than a quarter mile on average. So I want to represent all my data in measurements of about quarter-mile hexes, because that allows me to look at the data granularity at the same format for the people I'm actually building products for. It's a very nice thing to be able to do. So I already know I've got all this data, and at some point I'm going to have to start to have data scripts that will combine it all, and we'll do things like that. So this is kind of where we start to get away from the data gathering and going into the feasibility study. So I've gathered my data. Now I want to talk about the feasibility of doing this. So I still don't know whether we could do something with this. It's not yet known. But I know all the pieces are there. I know I have access to a lot of data now. So this is where the data scientists really mint their gold. They can come in and they can start to take this data on their local computer, translate it, integrate it, and begin to do studies to see, OK, can we actually build a map that would allow somebody to look at accessibility scores? So you can imagine, like, we have these hexes, and you might think like a person might want to like drag their mouse over a hex, and then there'd be like a little pop-up somewhere with a bunch of like metadata about that hex, and you could see if there was like I'm gonna do blue. If there was like a road going through this hex, and there was like a bus stop right here, you could shade this one a much deeper color, because this hex, which again is 1/4 of a mile, would have a much higher accessibility than this hex, which has no bus stop but a road, and would have even less accessibility than this hex, which has no road. So if you had a house, like let's say there was a dirt path that I didn't have data for going to a house right here, and there was some homes maybe like this and one home right there, I would say that this person has much greater accessibility to this transit stop than these two people and this person. And maybe in this very simple case, I'm thinking we could possibly tell these mobility managers that we might want to move the bus stop over to here because it makes it more accessible. That's what we're kind of talking about. It's like building a data product that helps these domain experts to make better decisions. Now, of course, this is a very simple case, and I want to be able to analyze large routes. I want to be able to analyze large geographic areas with dispersed populations. And I want to be able to also do this and possibly even suggest new routes. So this is now becoming a little bit of a machine learning project, too. So what are we doing on time? OK, so kind of move things along. Me and my data science team kind of went through, did a bunch of just like scrap data science projects for kind of just, with no real technical constraints. Just want to see, like, is it possible to kind of build things like this? Is it possible to create composite index scores? And there's a lot of technical challenges that you find when doing this you have to solve, and you have to solve them now at scale if you're going to build a data product around it. For example, it becomes very challenging when you have, at a 1/4 mile distance, you have hundreds of thousands of these hexes, and you need to be able to very quickly update the hexes with new data, because every hex through the H3 library has its own unique code. So we'll say, it's kind of like a UUID, so this is XYZ, and this is ABC, and this would be like, H12 or something. So each of these hexes has a unique identifier. And I want to attach a bunch of metadata to this hex. I also want to calculate some index score, which will tell me how to shade this hex. And that kind of gives us the transportation accessibility for that hex. So data scientists will go and build this at a small scale on their computer and see if they can make it work. Because if they can't make it work, they can't create these composite scores, things aren't making sense, or it doesn't even make sense to solve the problem with this kind of data or these kind of results, then we can just stop. And we can cut our losses, and that's perfectly fine. But you have to do these feasibility studies first before you start talking about like working in the cloud or doing things with building out architectures. You kind of have to do that first. But for sake of this lecture, let's just assume that we've done these feasibility studies and some of the data scientists have done those projects. Now we kind of get into, OK, we know we can do it. We've kind of sat down with the domain experts and showed them, hey, this is kind of the stuff that we think we can do. Is this interesting to you? Would this be helpful in your decision-making process? How could this inform your decision-making process? And you work through it, and you start to suss out these technical requirements. Like, OK, well, yeah, I want to be able to do it I want to be able to look at hexes for the entire North Country. And you're like, well, it might be kind of hard to display that many hexes in the browser at once. What if we just allowed you to look at like, a large, maybe like 10 square miles of a county at a time? Would that be OK? And so you have to kind of like work through these problems and understand the technical limitations before you can really begin to build an architecture out. So let's talk a little about architecture now. we have this data, and it comes to us in different forms, and we have to integrate it together. And then once we integrate it together, we've got to store it, and then we've got to use it while it's stored to display it to the user so they can make a decision. So this sounds a lot like a web application. And does everybody here know how the web works, more or less? If you take my Cogs 9 class, I've at least talked to you a little bit about it. So everybody knows you go to so just to give you a quick 2-second thing, you've got your browser window here, and you've got some sort of server living over here, and you've got a database. So when they say the back end, this is what they're talking about, the server and the database. And when you click a button, it sends a signal to the server. The server says, OK, what do you want? And then it goes to the database, says, give me this data. The data gets sent back to the server. The server says, OK, you wanted this data. You're going to do this stuff. And it sends the data back to the web browser. And the web browser updates with this new data. And this is more or less how the entire web works in 10 seconds. This is something like the arena that we have to build our product in because it's going to be web-based. I don't want to build a piece of software that somebody has to install on the computer. I want to build a website that somebody goes to and they uses this data product and it communicates with our back end. Now, the thing though that I really want to do though is I don't want to use a server because a server costs a lot of money. And I'm cheap when it comes to data products because AWS already makes a lot of money and so does Google and Azure. So I want to find like a serverless way to build this. So as far as, I think everything I've talked to you about so far might make sense. You're like, OK, I understand, or I got that. But maybe some of this architecture stuff might be kind of new to you. And if it is, that's great, because it's a cool learning opportunity. But I want you, and I'll try to put asterisks by the things I think you should know about. Like, don't graduate college without at least knowing what these products and what these services are and what their corollaries are on Azure. So everything will be through AWS, Amazon Web Services, but their corollaries on Azure and Google Cloud as well. Because when you go for a data science job, understanding how these products work at the web can be very helpful. And when we get to the end of this talk, I'll talk to you about why data scientists needs to know the end-to-end process and why it's important not to just know your little sliver of work, which would be like maybe these data science feasibility studies, but why understanding this whole process makes you more of a powerful data scientist and why it enables you to make better outcomes for the project and for end users once it's actually completed. So just really quick, we'll go very high level first, and then we'll go a little more in depth as time announces, or as time permits. So we have these different data sources that we have to integrate. So we already know we're going to have some sort of compute that does integration for us, right? Like I want to offload that. I'm not going to sit at the computer and press like a button to run every time new data comes through. This process needs to be automated. Once it gets computed, it's got to live somewhere. So it's got to live in some sort of database, right? And then I know that the user is going to use this product, right, from like a website. And so I know that there's got to be some sort of compute layer here where the website says, hey, get me this new data. And these are going to be kind of talking to each other. So this is kind of like the general, and then I should put this is user, this is more compute. And when I say compute, think of it as like a black box right now where data goes, it's like a function. Data goes in, something happens, and then something comes out. So this is like the architecture. At a very broad scale, that's what we want to do. And I don't want to put a server here. I want to do something serverless. We'll talk more about what that means in a little bit. And it also includes this compute area too. So in AWS, what we can do is we can store all of our data, not in an actual database like PostgreSQL or SQLite or SQL Server, what you think is a traditional relational database. We can store it in what's called a blob database, S3, simple storage system, I think. So Amazon S3 allows us a very general way to store whatever objects we want, and every single object has a unique URL to access that object. And when you update that object, as long as it has the same name, it keeps the URL. That's a really nice thing that we can take advantage of. So, and S3 is dirt cheap. Like this thing is so I run all of my classes off of S3, all of my PDFs, my guides, all of my data is in S3. And for like the last 2 years, I've spent, I think, like 12 cents with students coming and downloading crap from my S3 bucket for my classes. So it's very cheap, very stable. It's distributed across an international scale. It's very easy to get access to S3 stuff no matter where you are. It's not very slow. It's a very nice product. So, and this is definitely something that you're going to want to know about before you leave UCSD. So I want to store everything in S3, and I want to store it all as flat files, essentially. And when I mean flat files, I mean actual flat .json files. So remember, these hexes all have unique identifiers. That sounds like a good thing to use as a file name. So maybe I can have xyz.json. And I can have one of these for every single hex that we're going to use, which means potentially millions of hexes. But that's fine, because this is dirt cheap to store, and it's just flat files. And the JSON structure of this file is going to be all the metadata. It could be an accessibility score that we calculate. So accessibility score, we can say this is from 0 to 1. It could be a population could be here. All sorts of data we can store in JSON in here. And another reason why we want to do this too is if you ever took my Cogs 9 class, I think on all the Cogs 9 class we do this. If we've got two geographic areas, let's say these are zip codes. Zip codes are very large. Right, you have your midpoint, and let's say you have 2 points right here. Let's say you talk about socioeconomic wealth of zip code 1 versus 2. And let's say they're very proportionally different. What's more likely happening is that, yeah, this is different from this, but these two people in the middle are much more alike. And so if we can put hexes all throughout these zip codes, and the hexes that are on borders, we can actually take all the data in those zip codes, or in those or in those FIPS codes, or in the census data we get, and we can mash them together and kind of average them out, because the borders are much more alike than the midpoints of those zip codes. So hexes also give us a very nice way of kind of melding the data together in a way that can provide a little bit more deeper insights. OK, so we know that we want to store data like these JSON files in our S3. So how do we actually get this data into S3 and integrate it all without me having to do it manually every time? Well, there's something called Apache Airflow. Has anybody else heard about Apache Airflow? A couple people? OK, so this is something that you're going to want to know about. And we'll do a little mini, maybe I'll do it down here. Makes a little more sense. Time. OK, so let's say Apache Airflow. Apache Airflow is a directed acyclic graph network that runs pieces of code one at a time, and it orchestrates it in a way that guarantees that some things get ran in order. When you're integrating data like this, and you're doing transformations, normalizations, you're denormalizing, you're normalizing in some cases data, you're doing all these different configurations, you have to do them in lockstep and make sure that one thing happens once another thing happens. Some stuff can be parallelized, and all that Apache Airflow helps you do that. So all the data comes into here, and we have these steps. So one might be what's called an AWS Lambda function. Have you heard of a Lambda function? Okay, yeah. So if you have it, a Lambda function is just a piece of code that gets triggered, and when it gets triggered, it's kind of like a function. It does some compute that's pretty simple, and then it passes the data along. So there might be some very simple things in here that we want to do, which AWS Lambda functions can take care of. And then we might have those get passed on to a product called AWS Glue. Has anybody here heard of AWS Glue? A couple of people maybe. Glue is like a step up from Lambda functions. It's an extraction, transportation, or transformation load process, which takes data, extracts it, transforms it, and then loads it into another service. And so it does a little bit more complex transformations. But you have all these things going into this Apache Airflow graph, all these Lambda and Glue functions that get started and stopped. And at the end of it is it sends all the data for us to S3, and it organizes it for us, right? So this is really a key thing to do. Once I've taken all the data and I've stored it, because you always store your raw data. So in our S3 buckets, we have a directory for maybe let's say raw data. That never changes. Then we have a directory for processed data that we can use. And you can create many of these folder structures for data that gets processed and reprocessed. But we want to store all that in S3. And this is the compute stuff that happens. And it's all based on triggers. So whenever new data comes in, it gets triggered. And the reason why that's important is that if we're allowing a user to maybe provide a new route to try and see how that affects accessibility, we're going to ask them, give us a new GTFS file with your new route, and then we'll compute it for you. We'll store it here, and then when you load up your web browser, we might say like, oh, here's your new routes you want to try. Would you like to view them? They click yes, then that goes and gets the data from S3 and displays it. So I guess the other thing I haven't really told you about is what happens here. Because if we don't have a server, we have to have some way to get that data. And no surprise, this winds up being just another Lambda function from AWS. And when a user opens up their browser, and I don't want to talk about what happens here because this is going to be either a Vue or a React or like a Ruby on some sort of web framework to create a web application. And I don't really want to talk about that in this class, but you still have to create a web application to allow them to look at data. So let's just assume it's a React web app. Because we'll wind up using React or Vue.js, right? This is all HTML, CSS, and JavaScript. So once the user logs in and they're looking at their map, let's say that AWS Lambda function gets triggered, and it says, hey, we know that these hexes are currently visible to the user on their screen. It's called the DOM. Get us these hexes from these JSON files. So the AWS Lambda function will grab the specific JSON files that I want, and we'll send it back to the browser. And then the browser, which is a program, will know how to display that to the user. And then when the user shifts their map, it might have to load for a second or two, but then it will grab the new hexes and load those up as well. And so this is a very restrained operation, but it's a very cheap way of doing this. If we ever wanted to create a database and make it at scale much more complex, you can. But this is a very nice way to start. So this whole process here is kind of the architecture, and this is sort of the JSON was the data model that we spoke about. And so what I want to finish off with saying is how does this provide value? This provides value because it's a cheap way of doing this really quickly. It allows us to see if it works. We can always scale it up to make it better for more people. This provides value because in the real world, mobility managers are going to have a tool now that they can use, and they can run their own little tests and see if they're making new routes, how does it work, and how does it factor into accessibility. I don't have all the answers, and neither do they, but this is a big step in providing them a lot of data that they didn't have any access to or didn't know how to deal with before, and to provide them a workflow in which to use this stuff, and it's very easy to maintain. And as a data scientist, why it's important to understand all this is because people are typically looking to you as leaders in the technology field to explain to people and to understand this whole end-to-end process because, yeah, you might have to be in charge of doing data integration, and that's important. But if you understand what the user is doing with that data, and you understand where the data comes from, and why this is a model of a real-world data generating process, and one that's not particularly perfect, then even your initial feasibility studies are kind of useless if you don't understand how the user is going to use it. If you understand where the data is going to come from, like this is why data scientists get paid a lot of money, is because it's not easy stuff. And it's impossible in the 3 to 5 short years that you're in this place to learn all this stuff, besides all your Gs and everything else. So it really becomes on to you to go to these kind of lectures and find out about this stuff and learn about it. Try and do your own small projects. You get free AWS credit as a student. You can build small projects like this over time and play with it. Because when you go to an interview and you tell somebody, listen, yeah, I have this project I did for school, and it works, and it's correct, and I got an A. They're like, yeah, you and every other kid out there, but or you and every other adult out there, sorry. But if you can explain to them the value, explain to them, like, if this is going to be a real project, these are the concerns and considerations I would have. This is how you get value from this kind of project, and this is how it would help people. That shows a level of maturity that a technology leader should have. And it's something that's really, really important. And it's good signaling to people in an interview that you know your fundamentals, but you are also considering how those fundamentals work in the real world and how they work with people. And those are really important things to think about. I really wish that we could talk more about this for hours because it's a really interesting project to me. But the things that are interesting to me are the specificities and the small things that are not the main goal of what this talk was. The main goal of this talk was to introduce you to what a data product looks like. It was to introduce you to how you might want to learn about these things and to really think about the value that you get from understanding end-to-end process in a real-world data science kind of workflow. A project like this, really at scale, like I have 2 interns that are working on this right now, and we can build this. But just at scale and to really deploy it and stuff could take an additional 2 people. These are not easy things to do at all. but this is kind of like where you're going to work as an intern, or sorry, as a data scientist. Most of you will get attached to a data product team at a company, and you will do data science on the data product. And if you don't understand the end-to-end of the data product or not willing to learn, then your utility to that group goes way down. So I hope this is kind of like giving you some insight into what you have to look forward to and maybe have sparked some interest. But yeah, thank you so much. And any questions? Yeah.
Yeah, so you said your model is serverless, is that right?
Mm-hmm.
Is S3 not a server?
S3 is a data center, which has lots of products in them, and how you build your products is up to you, and you can build them with a traditional server, which handles requests, and then takes those requests and does stuff with them, or you can build them like a serverless function. So when I say serverless, this product becomes stateless. So when the user moves that map and then the new hexes come, it has no knowledge of the hexes that were there before. And in order to have state in a web application, you have to have a server because it has to do all that routing and it has to manage that state in the form of like models, like traditional like classes. And with AWS Lambda functions, you wouldn't have that state in there. It just says, oh, you want this new data? Well, here it is, and that's it. Does that answer your question?
Yeah.
Cool. Yeah.
Would you say that entry-level data analyst jobs and that kind of thing are a good starting point for gaining the skills necessary for a fuller career?
Yeah, I think data analysts is one of the best ways to start because as a data analyst, you have a lot more time with the domain experts because you're talking to actual, let's say traditionally business people who want you to run a report, who want you to work with the data at the high level. So you get a good understanding of what's happening with, like, let's say the business or what's happening with the product. And so that really enables you to see the value of the data and to see how it translates into real world things. Because as a data analyst, they're going to ask let's say some managers and say, hey, I need you to write these queries and build this data into a dashboard for me. They're kind of telling you the value because they know it. As a data scientist, it starts to become a little bit more on you to understand how do you translate that esoteric data into a real world value proposition. And for that, you need to have your own domain expertise and your own experience, and that comes with time. So data analyst is like a great place to start, even if you have a degree in data science. Does that answer your question?
Yes.
Cool. Yeah.
Since AWS does stuff on like a pay-as-you-go model, and considering how many places of uncertainty there are with projects like these, how do you budget for something like
Yeah, so budget is great. When I was in grad school, we had teams for our thesis project. One team blew through $6,000 worth of funding overnight by spinning up a bunch of compute clusters for a deep learning project that they were working on. So AWS has gotten a lot better at cost stuff over the years, but they have one thing where they have a cloud monitoring, so they can tell you how much it's costing, and you can set limits for, like, if you reach $100, send me 30 emails, or wake me up, slap me in the face. Ultimately, though, if you go with something that's serverless like this, it only runs when there's a change. And so if this was instead of S3 a real database like AWS RDS, then that RDS thing's costing me every second it's running, and I have to manually turn it off. So in those cases, yes. I will say as a student, if you have free AWS credits and you wind up incurring a cost, you can talk to them, and they're usually pretty good with like saying, just don't do it again. But yeah, always, don't do any of this stuff without having like monitoring on and without understanding the potential costs, which is, again, another important part of being a true data scientist, because I got to come up with a budget for this project. And if I go past the budget, then people don't eat. That person usually winds up being me. So you definitely want to make sure that you're keeping true with the costs. So good question.
I've got a question, Kyle. So some of the students here are asking questions about details with S3 or various things like that, serverless, whatever. These are the students that already have a strong idea about how data science tooling works. Maybe they've played with it. But the vast majority of students sitting here are not asking questions right now, in part because they don't even know the question to ask. Because what this class does is it gets them some statistical knowledge and some data viz knowledge. But we haven't yet provided them with the education to really think about these problems. This is what you're giving them, is their first glance at the architecture and tooling that really happen.
Sure.
So for those students out there that don't even know the questions to ask, what advice can you give them on how to get that information?
start reading. It's really easy as an undergrad to fall in. I was an undergrad, so is Jason. So we've been there, done that. It's really easy to fall in the trap of I'm paying an exorbitant amount of money for an education, and they're going to give me everything I need. And I'm going to go to class. I'm going to get an A+. I'm going to walk out there, and I'm going to be prepared to do real work. And that's unfortunately just not true, especially in a place like data science, because it involves so many different facets of technology. So you really want to go online. One of the best things you can do is find engineering blogs from real companies like Uber Engineering Blog, other engineering blogs from companies like Google, and read what their data scientists are doing, what their data scientists are working on. And when you don't understand something, go look up the term and start to amass some knowledge, and then go ask people. Go to CSC people, go to a professor, say, hey, how does this work? Come to talks like this and ask questions. But you have to be responsible for your own education because nobody ostensibly cares more about it than you do. So you have to be willing to go out there and extract out that knowledge and information you need. And the only way to do that is to start hunting and gathering. You just can't be a passive observer.